Suppose I have a function f which is positive and x takes values in some finite set A. So, size of the set is finite. Associated with f, we will consider the following distribution: e to the power minus beta fx Now, if I am given any probability distribution on A, this is surely a probability distribution on A, right? Why? Because this is positive and it adds up to 1 by definition, right? I have normalized it by the sum. So, this is a probability distribution. So, this is a probability distribution on A. Now, I claim any probability distribution on A can be written in that form with the proper choice of f. Let's assume that my probability distributions are such that they put positive probability on each element of A to make things simple. Because otherwise I can reduce A, right? I mean, if some elements of A are not having positive probability, I'll just discard them, okay? So, let's say I have a probability distribution on A which puts positive mass on each and every element of A. I claim I can always represent it in this form with the proper choice of f. What should be my f? What should be my f? You can't see the f there? Suppose Px is the probability for x. What should be the f? Give me one choice. And beta is a constant. So there is a choice of here. Yes? Negative of log of Px. That will work. I didn't say that the choice of f is unique. Okay? There are many choices of f. Okay? So given any positive function f, I can create a probability distribution on A. Given any probability distribution on A, I can create this function f, okay. So this is an idea that goes back to, again, 40s and 50s, when this mathematical physicist working on thermodynamics was looking at this distribution. This is called the Gibbs distribution or Gibbs-Boltzmann distribution, okay. And they called this f something like the energy function, and these x's were different states they were talking about, and this was the probability of the state. Okay. And this beta is related to temperature of the system. Okay. So they actually write beta in terms of absolute temperature, but I'm not doing that. Okay. So for us who are doing mathematics and probability, this is a much simpler and easier representation. So this is called the Gibbs distribution associated with the function f. Now this function has a very interesting property, that if the value of f is small, then this distribution puts more weight on that or more probability on that. That is clear, right? Because of exponential minus beta fx. So if I am sampling from this distribution, in some sense, those values are more likely to be sampled for which f value is smaller, right? So to mathematical physicists or those who work on thermodynamics, that's nothing new. They are saying that, okay, all that it means is that if I have a state, so this is the energy function. So it is the low energy states that I am picking up. In the low energy, things sort of stabilize, so they have more likelihood. Okay, that's what they say. Okay. As we take the break for half an hour, this is an exercise for you. Think about what happens to this distribution when beta is large and beta is small. Beta is a positive constant. Beta is also a positive constant. What happens to this distribution when beta is large and beta is small? Okay. So now we take a break for half an hour and you think about this. So I have asked you to think about two things. That invariant probability distribution, from where it is coming, and this one.
Okay, so let's thank Chaudhuri for very nice